Hi, everyone. So I'm going to be talking about Apache Kafka and even more about logs, which is one of my favorite subjects. I think a friend told me actually I'm kind of like one of these paleo diet people that whatever the subject is in the conversation, I kind of always end up coming back and talking about how whatever we're conceptualizing building, it could be built on some kind of log structured data flow. And so that's going to be the subject of this discussion. And specifically, I'm going to be talking about data integration. So I'll introduce that first because it's kind of an odd phrase. In fact, I would say actually it's kind of a boring subject. I hesitate always to give a talk on this because I think, well, nobody really wants to hear about data integration or ETL. But in reality, I think it's incredibly important. So I started at LinkedIn really in kind of the relevance space, really using data, kind of the algorithmic uses of data, and I kind of fell into the infrastructure space really in working on making some of these things possible. And what I've seen is that this is very often kind of the big critical problem that holds things back. And so what I mean by this, by data integration, is really getting all your data available in these powerful processing or infrastructure systems where you can really make use of it. And I mean it in a large way, like everything from how data is transported to how it's modeled and all that kind of stuff. I'm really going to focus on kind of the capturing the lowest level in this talk. So kind of my conceptualization of this problem is a lot of people may have heard of Maslow's hierarchy. And so there was this psychologist called Maslow, and he kind of felt that human beings had this hierarchy of what they needed. The lowest level is kind of physiological needs, your food, clothing, shelter, and then safety and love and belonging all the way up to self-actualization, which is kind of your long-term hopes and desires. And his observation is when the lowest level of the pyramid isn't there, when you don't have food, clothing, and shelter, you're not thinking about self-actualization. But when you do have those things, you kind of forget that they're there and you don't think about them too much. And I think this is exactly how data integration fits in. So if I were to make a similar chart for data, I would put the acquisition or collection of data or the semantics of your data kind of at the heart of the problem, the base of that pyramid. And then the things that people initially gravitate towards, automation is kind of this higher level need. Yet when I talk to people about how they're approaching data problems, and actually this is true even for myself when I first started doing this stuff, you kind of jump right to the end state, right? So your interest is really we're going to run these deep learning algorithms and we're going to do all this cool fancy stuff. But usually what's actually holding them back is not the sophistication of the algorithms, but actually like they're FTPing CSV files around, and it's totally unreliable, and they don't have the right data. And so that's kind of the problem I'm going to address. My observation is that this is very much like a pyramid. So when you've really mastered data flow and that is fully reliable and timely and you model all your data correctly, you kind of forget about it and you focus totally on using your data. But when that's missing or when that breaks, you'll focus on nothing else, right? So a lot of these kind of really fancy new data infrastructure systems, they're not inherently useful unless they have data in them, right? A Hadoop cluster, it doesn't do anything if the data in the Hadoop cluster is wrong, right? Like you can only compute wrong things. It's kind of a very, very expensive space heater or something. So I'm going to talk really, that's kind of my motivation in talking about data integration. And I want to just kind of introduce the problem a little bit. I think the first question is really why is this even a hard thing? What makes this hard? Why isn't this problem already solved long ago? And I think the answer to that is really that two things. The first is that the type of data that we care about has really changed dramatically, maybe in the last 10 years, 15 years. I think if you were to ask companies what they considered their data to be, 10, 15 years ago, they would have really talked about transactional data in databases. So that first bullet point. They would describe their data as, our users, our products, our, orders, whatever. But now I think a lot of companies are really seeing the value of, the rest of the data that they may have, right? And this is really event data. This is, maybe user activity data if you're a website, right? Clicks, impressions, page views. That's what kind of Google's fortune is built on, right? Click-through rate. But it's also, metrics, application data like CPU usage, requests per second, errors, all this stuff that kind of lets you run your business. And this is expanding even further, right? If you're one of these futurist types and you're really into like the Internet of Things and all the instrumentation that's going to be out there in the physical world as these things become more digital. And so as this data, the type of data we care about has changed. That's really changed the problem, right? This sensor or event data is actually extremely high volume and really different from what traditional databases deal with. So that that's actually made handling data much harder. And the second problem is I think there's really an explosion of data systems. I mean, what's happened here is the transition to distributed data infrastructure has been really disruptive. And so you see a ton of really interesting, useful, powerful systems that do one thing really well. So rather than a general purpose relational database, or in addition to that, you're seeing a lot of really cool specialized systems that handle different problems. And this looks different at different companies. But at LinkedIn, if I were to categorize the things we have, I took some sampling of our infrastructure. We have these key value stores like Voldemort and Espresso, and they're really good at low latency live serving. We have a graph database, which is really good at finding connections between people and these traversals and distances. We have an OLAP system, which does like kind of reporting, counts and graphs, that kind of stuff, both customer facing and internal. We have a monitoring system which does kind of all real-time alerting and operational trending and whatever. We have a search system, and then we have an offline ecosystem. And really, this is just a sampling of the types of systems we have. If I were to give a full list, it's actually much larger. And each of these ends up needing data, right? To be useful, it needs a feed of data. And its use, the degree to which you can make use of each of those pieces of software is determined by how easy is it to, get the data you need into it. And my engagement in this problem, or my understanding of this problem, came about really gradually, right? So I started with Hadoop at LinkedIn. This was one of the first kind of large-scale data integration problems I had. I was interested in rolling out Hadoop at LinkedIn. This was a long time ago, and so we got money and we got a Hadoop cluster, and we thought, okay, great, we're done. And then we realized we didn't have any data in our Hadoop cluster. And our goal was to take on some of these recommendation problems, to compute people that you might know, or people who viewed this profile also viewed that profile. And so our budgeting of time was, well, we'll spend about 80% of our time on these algorithmic problems, and we'll spend about 20% of our time getting data in to feed it and getting data back out onto the live site to serve it. And in reality, that ended up being totally inverted. Right? In reality, we ended up spending a ton of time trying to get reliable data flow in and reliable data flow back out, and much less time on the actual algorithms. But it turns out that data flow was actually time really well spent. And the reason it was so well spent was once you have that data, it becomes a basis for all kinds of other things. And so, in a sense, I came to realize every hour we invested in data flow was actually powering a lot of new things we hadn't even thought of in the Hadoop infrastructure. But at the same time we were doing this, we were starting to make use of other systems for real-time data computations, right? So we wanted to show people who had viewed your profile. We wanted to show other kind of activity data on the live site, and that wasn't going through the Hadoop layer. That was a real-time computation, and so I kind of saw us doing this, in two different places. We were copying a set of data into Hadoop, and we're trying to do real-time capture and processing on essentially the same data. But what we actually had was we had different, pipelines or way of copying data for each system, right? So we built a custom way of rsyncing log files into Hadoop for processing. We built custom database extraction, and then, for live processing, we had a totally different way of capturing these with services and other things. And when I looked around more broadly, I saw that we were actually doing this all over the place, right? The way it works is every time we would get a new system, like a monitoring system, we would think, okay, we need to get data into this system. How are we going to capture, monitoring statistics so we can feed it in? And because you kind of approach this almost in an ad hoc way, you end up building these individual lines, in this slide from each system to each other system, for each data source to each other system. And over time, you get closer and closer to full connectivity, right? So where you have, in some sense, n squared pipelines. And the problem with this is it turns out that each of these pipelines is actually much harder than you would imagine, right? Because it turns out that data flow needs to be incremental. You can't copy the full data every time. It's too big usually. And that means that your data flow has to always be correct. If it gets messed up even once, it'll be wrong in perpetuity. You'll be missing rows or missing events or missing whatever. And you need to be able to verify that the same data is in each of these systems. You need to be able to track it. And then there's really different requirements for different systems. Like the Hadoop data flow was this kind of very high throughput batch thing, whereas the live data flow was a low latency thing. So anyhow, this was kind of the path we started down, and I realized at a certain point it was untenable, right? Like we had a small portion of data available in Hadoop, and we were actually probably never on that path going to get to full connectivity, to get to even just full data in Hadoop, let alone full data available for the real-time systems. So what I'm going to advocate is actually some kind of centralized strategy for data integration. And I'm going to advocate a particular approach to this, right? In a sense, this talk is less of a Wikipedia article about Kafka, and it's more of an editorial about how I think you should manage data. And I'm going to advocate an approach that's based around a real-time log, right? And what I mean by that is, every system that has data or maintains data or produces data publishes it into some kind of central log, and every system that is a analytical system and serves data subscribes to the feeds that it needs and indexes them for serving, right? So our Hadoop system might subscribe to all our data sources, whereas maybe our monitoring system only subscribes to the few that are relevant for monitoring, and search subscribes to the things that are indexed for searching, and so on. So this is what the high-level talk is going to be about this kind of larger data integration problem, and in particular the relationship of that problem to logs, and in particular the relationship of that to a particular set of infrastructure we've built called Kafka, which is what I'm going to talk about next. So I've introduced kind of the integration problem. Now I'll talk about the infrastructure we built, and then I'll talk a little bit about the relationship between the two things. So Kafka is it's a messaging system. This is usually how I explain it to people. In a messaging system, you have producers. They send messages or events or records, to a central broker. In this case, it's a whole cluster of machines, a Kafka cluster. And then you have consumers who subscribe to those. And in Kafka, all of these feeds are real-time feeds. All of them are multi-subscriber, meaning you can have 0 people consuming a feed, or you can have many people consuming a feed. And each stage of this is distributed, right? The assumption is your producers are spread over many machines. Your Kafka cluster is spread over many machines. And even these individual consumers, though I've kind of drawn them as boxes, a consumer may actually be a distributed system itself. It might be a Hadoop cluster or a search cluster. So that's kind of the basic setup and the basic thing we've built. And yet it is really different, right? The implementation of Kafka is extremely different from a traditional messaging system. And in large part, that's what makes it possible to handle the broader scope of data integration problems. I'm going to talk a little bit about how it's architecturally different and how that actually plays out. And for people who are using AWS, using Amazon, there's actually an equivalent service which is very, very similar, which is new, called Amazon Kinesis. And that's actually very, very similar to Kafka. I mean, I think they were probably inspired by Kafka to build some kind of stream or feed serving thing, and the APIs look very similar, which was something I was super happy about because my first project at LinkedIn was actually a clone of Amazon Dynamo. So not DynamoDB, but their research paper on Amazon Dynamo. And so it was a little bit derivative. And I was actually glad that you can kind of share back and forth. And they have a Kafka-like web service, which in some sense is kind of the highest validation, I guess. When there's an AWS service for whatever you came up with, then you can feel like you've really made it. Yeah, now there's almost like a class of these things because there's two. And so most of what I'm going to say about Kafka is equally true of Kinesis. And the advantage, of course, of Kinesis is they'll host it for you. The advantage of Kafka is maybe it's a little more featureful and you have more control over your data. So let me give kind of a brief history of Kafka and how we came to build our own messaging system, which occasionally people tell me is a little bit crazy. The way that this actually came about was, as I said, I was responsible for kind of Hadoop loads as well as some of these real-time data products, and I was finding that all of our time was spent on just shipping data around from place to place. And I and several other people on the team had kind of an infrastructure or database background, and so we really felt like, hey, this is a problem that could be solved in infrastructure, right? This is a problem that we could build a system for rather than just building more scripts or higher level things. And what we saw was there was actually some reason or motivation for each of these different pipelines. Each of them kind of solved a different portion of the overall problem. So the way that we copied database data around in real time, there was actually some sense to that. And the way we took CSV dumps for ETL into our offline systems, there was some motivation for why that was good at what it did. And even our we had like some ActiveMQ queuing systems. Those were good for what they were being used at. And we realized there was actually a kind of rich set of needs. And if you wanted to go after this, you would have to really be able to do all of these things, right? And to be able to get any kind of consolidation, you would have to be able to have kind of the best characteristics of a lot of these things. And so we originally started out by actually just taking ActiveMQ and saying, well, this is a real-time thing. Maybe we can move all of our offline data copies into this. And we found that didn't work that well, primarily because it turns out most of these message brokers are not really aimed at high throughput data loads. I think they're not really originally targeting logging or event data, something where each page view of a large website might produce many, many events. And so we found there was just all these problems, right? They don't handle persistent data well. So if your Hadoop cluster goes down for maintenance and it needs to come back up and load the backload of data that it hadn't loaded, that wasn't going to work. Like the whole message cluster would fall over. And I think at the time we looked at this, we realized we would have needed about 300 ActiveMQ brokers. And at the time that we were doing this, this was a long time ago, we actually only had 300 machines for the whole site. So you can imagine the economics of having 300 logging brokers for 300 serving machines are probably not very tenable. And yet we were able to do this problem with our very primitive files and rsyncs and data copies that we were doing ETL with. And so there was this huge throughput gap between what a messaging system was able to do and what kind of raw file system copies were able to do. And so we thought more about kind of what our needs were. We really came up with 3 design principles of what we thought a messaging system would have to do. So the first is, we thought you really need one pipeline to kind of rule all of these. If you can't consolidate them and you have to build something special purpose for each, that's going to be a ton of work. And I'll talk a little bit about what those characteristics are that you really need to satisfy. And the second was we thought there was really an opportunity to support the processing of messages better. And I'll talk a little bit about that kind of towards the end of this talk. But in a way, what had been done in this real-time infrastructure area was just kind of message brokering. These systems will hold on to your messages, they'll hand them out, but that's it. They don't support any kind of richer processing layers. And we were using Hadoop, and we felt like, hey, in a way, Hadoop is actually doing something much higher level. In addition to giving you something like HDFS, it allows you to really do MapReduce processing on top, and now even other kind of processing frameworks. So we felt one of the key characteristics of a messaging layer was to be able to really support stream processing, to be able to support real-time processing of the data that came out in a rich way, right? And to be built in a way that would support that higher level framework on top. And I'll talk a little bit about that in a bit. And the final point was we really wanted to design around clusters, not servers. So one of the characteristics, I think, of modern data infrastructure is that you don't think very much about the individual machines, right? So whenever a distributed system has really succeeded, I think you think about the cluster, right? This is true of HDFS. You don't think of writing data to individual data nodes. You think of writing data to the HDFS cluster, right? You think of processing a file which is spread across many individual machines, but you don't think about those machines individually, right? And that's not really true of traditional messaging systems where you think of individual brokers and connecting to this broker. They are somewhat distributed, and they send data back and forth over the network, but still you don't manage them or expand them as a cluster. Your queues and topics are kind of on a particular machine, and we wanted to be able to scale that across a cluster of machines and think of the machines in some sense as an implementation detail. And so that kind of came up with that kind of led us to the design and characteristics for Kafka, which were first to have the scalability of a file system. You should be able to get throughput, which is competitive with logging or log copying or any of that stuff. Be able to give guarantees similar to a database, right? So messages are strictly ordered. This is really important for any kind of database feed where if messages get reordered, you may have two updates to the same row which come out of order, and then you store a previous value instead of a later one. And then also distributed by default. And in practice, what this means is you have a replication model so that any individual machine can fail without any data loss, and a partitioning model, meaning you can transparently scale your cluster by adding machines without disturbing the applications that are interacting with it. So these were the characteristics that we came up with that a messaging system that would kind of wipe out all of these ad hoc pipelines would have to have. And indeed, we built this, and it's used at LinkedIn, and it's used really heavily. It's kind of the backbone of data transport or data integration. So we have at any given time around 175 terabytes of data that's in flight and flying around in each data center. It's low latency, so it's totally suitable for real-time messaging. It's a few milliseconds to publish and then consume a message. We support replication between data centers. And it's used at very large scale, right? We have thousands of data producers and thousands of consumers, and millions of messages read and written per second. So it's this kind of messaging fabric at LinkedIn. And it's well integrated with Hadoop, which was one of my goals since I was running that team. And the full process of getting data into Hadoop is totally automated. If you publish a new Kafka feed, it will show up automatically and immediately in Hadoop. We'll create Hive tables off the metadata we maintain around that data, and that's all kind of done without talking to anyone or filing a ticket. It just happens. And this is kind of a critical component of doing this. Previously, for database loads, we'd had actually a whole team of people that worked just on maintaining the loading of data. And after this, it was really kind of half-time project for somebody, and they were really only involved when that piping broke. But of course, we did have people working on Kafka, so it wasn't like we got out of the woods totally. Okay, so that's Kafka. So now I've introduced the data integration problem, and I've introduced Kafka, this piece of infrastructure. And I've talked a little bit about some of the characteristics of Kafka, but now I want to talk about kind of one of the central abstractions Kafka provides and how it helps this data integration problem. And I think this is a really different way of thinking about the data that you have and thinking about how you model and transport it. And this is as a log. So the abstraction that Kafka provides is a log. It is a log-centric system. In the same way that a relational database provides tables, Kafka provides logs. So in order for that to make any sense, and in order for me to clarify how that would help you, I need to first talk a little bit about what a log is. And I have a very particular meaning for that in mind. So what I actually don't necessarily mean is what people most often think of, which is an Apache log, a text file with a bunch of lines of text in it. And people probably know Apache logs, right? It has the URL, and it has whether it was a GET or a PUT or a POST, and it has the timestamp, and it kind of logs all the access to your Apache server. And this is a little bit primitive compared to what I mean, right? So there's clearly some structure to this data. You can see it's like an append-only file. So it's similar to what I mean, but I actually have a more abstract view of what a log is. So to me, a log is a structured array or feed of messages. So it's ordered. It's immutable, meaning the records don't change once they're written. And it's ordered kind of by time. So the newer writes happen at the end, and you can denote each record in a log by some number. And I've shown the records here as these little rectangular boxes, and I've given them each a number, 0, 1, 2, 3, 4, and that would sometimes be called a log sequence number, or in Kafka we call it the offset, which is also a common name for it. And so you can kind of imagine the Apache log being this type of a log as well, right? If the older lines were on the left and the newer lines were being appended on the right. But I think this view of logs kind of abstracts over the fact that they're denoted by new lines or how the columns inside of it are particularly formatted. So the records here, they contain data. I haven't said how the data is structured, and for most of this talk I'm going to ignore that critical problem. So we can assume that the contents of a record are like maybe JSON or protocol buffers or some formatted record. It really doesn't matter. Let's just say it's your data. And you can imagine each one of these boxes containing one Apache log line. And so if you think about it this way, this is almost an abstract data structure. And it's a little bit different from just a text file, which is almost like one potentially bad implementation of that data structure. And if you wanted to scale out a log, one way you could do this would be by partitioning it up, sharding it into multiple shards or partitions. And if you did this, that would be exactly the data model of Apache Kafka. This is exactly the abstraction that Kafka provides. So we have a notion of a topic, which is like a category of data. So at LinkedIn, for example, page views are a topic, searches are a topic. Each kind of large category of data is a topic. And inside of that, data is maybe cut up maybe by user ID or something like that into partitions. And each of these partitions is really just a log or sequence of records. And we're continually, as events occur, we're continually appending it to the end of these logs. And then we have some way of maintaining data. Either we maintain it for a week, or we maintain it for all time if that's possible, or whatever. There's some policy around how data is maintained. But this is what I mean by a log. And so the question you would ask is like, well, that sounds great. I have Apache logs, but how is that a messaging system? Since originally I said that Kafka was a messaging system, and since after all our job here is to get data, from data sources to data systems. And the answer to that is logs turn out to actually be a fantastic mechanism for implementing publish-subscribe messaging. So I've kind of illustrated this here. I have that logical picture of a log, and I have a data source, which is appending new records to the log. And here I've kind of drawn two boxes, for a system A and a system B, which are subscribing to this log. And this is actually really different from how messaging systems work because there's only one log, no matter how many subscribing systems there are. I could have 1,000 subscribing systems. I still have the same amount of data. So I'm not maintaining a queue or whatever per reader. And everybody sees the data in the same order, which is the log order. And more importantly, I actually have this log sequence number. And this is a really subtle point that I'm going to make, but I'm going to come back to it a couple times. The log sequence number, in some sense, it acts as a sort of time for the system, which is not tied to physical time, like, oh, it's 9 o'clock. But in some sense, you could say system A, if it has read up to record 7, it's at time 7, right? And system B, if it's read up to record 11, it's at time 11. And this actually ends up being really important because you can reason about the state of system A and the state of system B by how much of this log they've consumed. What number are they up to? This turns out to be a really important property, and we're not the first people to discover this. In fact, we didn't invent it at all. This is actually a really common thing in distributed systems. So, the reason that we had this really weird notion of what a messaging system should look like was in large part because we were coming from an infrastructure background where, logs are at the heart of a lot of these data systems. So I'm going to give a little bit of an example here. I'm going to kind of delve a little bit into the use of logs in distributed systems, and I'm going to do that hopefully to make a larger point about data integration. So I'm going to go a little bit into the theory, and I promise that there'll be a point to it all. So let me start with that. I mean, I think most people have at least heard of, if you've used MySQL, you've heard of, bin log replication. And this is a really traditional mechanism that databases replicate data. But it's not just relational databases. It's also non-relational databases. Like for example, HBase is built on top of a log, which is maintained on HDFS. And even inside of HDFS, if you were to go to the HDFS name node, there's a log of changes. And in more recent versions of HDFS, that log is even a distributed, replicated log to try and make it, fault tolerant. So logs are kind of everywhere we look, and even in newer Google infrastructure like Spanner, or you might read papers about some of these things, you find over and over again they're built on top of logs. And so this idea just keeps popping up over and over again. And I want to talk a little bit about what it is fundamentally about, right? So recently, Leslie Lamport won a Turing Award, and it was actually in part for his work on an algorithm called Paxos, which is a consensus algorithm. And a consensus algorithm is one way that you can kind of maintain agreement on a distributed log. And there's actually a number of these, including Raft and other things. And they're implementable things which allow you to implement a fault-tolerant distributed log. And it turns out this is such a fundamental thing and used in so many different systems that we're actually gave out a Turing Award for it, which is pretty cool. And so I'm gonna actually show an example of how logs get used in systems, and then I'll tie that back to our data integration point. At a high level, to speak broadly, logs are used for two purposes. First, they're used for replication, right? They're used to get data from point A to point B to replicate data. And second, they're used for consistency, right? They're used to bring multiple systems into agreement on the ordering of changes, which makes sure that those systems, remain in the same state. So that's an incredibly abstract statement. So let me give a really practical, hands-on kind of example. This is a toy example. I'm going to try and build a fault-tolerant distributed hash table of CEOs. So I'm going to try and maintain a mapping from company name to CEO. And if I was maintaining this on only a single server, my problem wouldn't be too hard, right? If my server died, I would maybe lose my hash table. But other than that, I don't have too many problems. But if I want to replicate this, in other words, I want the same data to be on multiple machines, and I want to issue real-time updates to that data, right, as CEOs change, then I have a more complicated problem because all kinds of bad things could happen, right? I could lose, network packets. One of my machines could crash and come back. There's potentially concurrency problems. All kinds of things could go wrong, right? So let me walk through this problem, and then I'll demonstrate kind of how a traditional solution to this problem would work using a log, and then we'll tie that back to our larger topic. So to understand this slide, on the left, I have a list of changes to my hash table. So my first update is I'm putting as the CEO of Microsoft, Bill Gates. And I'm putting for Apple, Steve Jobs. And then Microsoft gets updated to Steve Ballmer. Google gets Larry Page, and so on and so on. And down at the end, you see this very fast succession of updates for Yahoo as they go through different CEOs. And you can imagine exactly the kinds of things that could go wrong here, right? If these updates are going to my two replicas down here, replica 1 and replica 2. You can imagine if one of my replicas crashes or stalls or whatever, when it comes back up, it will have lost updates. It will have missed some of the updates that went to the other replica. And so they won't have the same state on them. The kind of final state I'm expecting after all these updates is over on the right, which is the current CEO of each of these companies. So how can I guard myself against these kinds of problems, right? I lost updates problem, the updates were reordered problem, any of these problems. There is actually a traditional solution to this in distributed systems, which is to have a log of changes, right? And by a log of changes, let's go back to that log array of records I drew before. The log of changes is just all the updates to my hash table. So I've turned all those put operations on their side, and I'm now feeding them into these two machines, right? And I'm feeding them in log order. So this is a way that if I could somehow magically implement this log, if there was some algorithm or system that would give me this magical log, then I could keep my two replicas totally in sync, right? They would each apply the same updates in the same order. If one of them comes down, crashed, it would come back and apply, updates from whatever point in time it happened to have data for. So this also gives me a way to reason about the state of these two systems, right? I can say, hey, one hash table has read up to offset or time 10. The other is caught up to time 12. And so I can make sure I don't serve any kind of stale data because I know what the newest write is and what each of my replicas is up to. So this is kind of the traditional use of logs. And this ensures that I don't reorder the updates so that, for example, Scott Thompson doesn't sneak in after Marissa Mayer and end up as the permanent CEO of Yahoo or whatever. And it also makes sure that whatever happens to my individual replicas, when they come back up, they get everything in the right order, even though physically the time that they're applying these updates is much different. Okay, so that's the theory of logs. That's how they're used in distributed systems. There's two kind of high-level design styles that if you were to Google around and look at logs in distributed systems of how this is used, I showed one which is more like state machine replication, where we're replicating all the commands and each peer is applying those changes to itself and serving reads. There's also another style where maybe we elect a master and it controls the updates to the log. But to a certain extent, I'm not going to focus on that at all, except to say that there's a ton of ways of using this log concept to design a distributed system and to reason about the consistency and correctness of the system. Okay, so that was kind of an excursion into theory. And the reason I did that was because I want to actually make a broader point about the use of logs for data integration. And to make that point, I'm going to actually start with just an example of how this plays out at LinkedIn. And so this is one small snapshot of that larger system picture I drew. So and this example is about serving jobs. So a really simple thing that LinkedIn has done for a long time is we have jobs on our website and we want to show jobs to people. So you come and maybe you see a job you're interested, you click on it, and we have a page that tells you about the job and what company it's at and so on. So it's kind of the simplest thing a website could do. But over time, something like this actually becomes much more complicated, right? You end up needing to do analytics on jobs, right? So maybe it needs, the fact that a job view occurred, it needs to go into your data warehouse. People end up kind of attacking your website and trying to crawl and scrape all your data or submit fake jobs or otherwise abuse you, right? So you end up with some kind of security apparatus to control, bad things. And everybody on the internet has something like this. You end up needing some kind of external reporting system for people who are posting jobs, right? They're paying you money to post jobs, so you need to tell them what value they got. And then it turns out that you want to recommend jobs to people, so you need to know the click-through rate of different jobs and who's viewing them and so on. And finally, if this is part of your business, you probably have some kind of monitoring that needs to be done that, hey, indeed we're serving lots of job views right now. And so all of these different functions, if you kind of embed them into the job viewing page, the job viewing page becomes increasingly complicated. And since those functions are actually shared by many things, and jobs might be viewed on iPhones as well as a web page, getting all that stuff right in each place becomes really complicated. And so the way that the kind of way you can handle that data integration problem is by just having the thing which serves job views publish a stream of what happened. So it just says, hey, this job was viewed by this person, this job was viewed by that person. And that feed is available for every one of these systems that needs to subscribe to it and handle that data in different ways. So this is a really practical example of what I'm talking about. Coming back to our larger picture, how does that relate to logs? Essentially the approach to data integration I'm advocating is that all of these things, right, all of these different applications, all of these different distributed serving systems, in some sense they're all one big distributed system. right? And so as one big distributed system, they have exactly the same replication and consistency problems that a traditional database would have. It's just they have it in the large. You can think of in some sense the whole company's data infrastructure, or the whole company's systems are one big distributed system. And this kind of commit log is a way to keep everybody in sync on the same set of data as that data changes and in real time, right? So that's kind of the larger style of how you can use a distributed log to keep all your data in sync. How does this compare to what people kind of traditionally do with data? I mean, I guess I'm kind of aware of two other ways of doing data integration that we were doing previously, right? Copying files around and messaging, right? So in comparison to file copying, this log is really a kind of real-time multi-subscriber thing, right? So data can be delivered in milliseconds, which is hard in a file. Typically, you fill up the file and then you copy it over for processing, right? And it's also much easier to make a multi-subscriber system. So if data is going to many places, it's probably a little easier than copying all the files around to everyone. And in comparison to like traditional messaging, at least, this is really aimed at large data, right? So the fact that we have a single log of changes rather than the implementation of a normal messaging system, which has a queue per subscriber, is really important. The fact that we support large persistent data is really important. These end up being kind of critical aspects of really scaling this out for large event data in addition to kind of smaller database or transactional data. So that's kind of the high level of how you can use a log for data integration. Now I'm going to move on to one more topic, which I think is very closely related. So I said that one of the things that we were interested in designing Kafka around was this idea of stream processing, that there would be a processing layer that would run in real time on top of your data feeds. And this is indeed something we've done. And the way you can think about this is, in some sense, if you view your whole set of systems, all your databases and all your applications as one big distributed system or one big distributed database, and if you view Kafka as a kind of commit log for that database, then in some sense stream processing is a trigger or a materialized view system for that, right? So it's a way to compute new things off of those feeds. And it's a little different from MapReduce or in large part because it's a real-time processing system. So I see this as, in some sense, the next evolution of message processing, where a message processing system is relatively low level. A stream processing system is actually trying to give you a much richer set of semantics and the ability to kind of control distributed processing in a way that a messaging system doesn't. And so I want to kind of make a case that this is actually a really important part of the data integration problem as well. This is actually a slightly difficult point to make. A lot of people think of stream processing as almost kind of a niche application, but I actually don't think that that's true. I mean, what we've noticed is as our data has become real-time, our processing needs have naturally become real-time as well. And I think this isn't an accident. If you think about something like the U.S. Census, this is an example I like to give people. The U.S. Census is, it's like kind of the prototypical batch process. We go around every 10 years, and we go door to door, and we count each person who lives in a house. And at the end, we add them all up. And this methodology always seems really crazy if you describe it to a software engineer. If you describe it to a software engineer, they'll say, hey, that's a really weird way of figuring out what people we have. Why don't we just journal all the births and deaths? And if we did that, then not only would we know how many people we have right now, we would know how many people we had at every previous point in time. And that kind of is exactly the difference between a batch process and a stream process. So I think this is actually like a very general mechanism. And so you might wonder, well, why don't we do that? And the reason is actually pretty obvious, right? Like the original census was done by people on horseback, right, riding around and writing in big binders of paper that they had to kind of like ride on horseback to some central place to count. And so it's very natural that you would do kind of batch processing if you're riding around on horse. There was no high-speed computer network, so the other alternative wasn't really possible. And this is exactly what we found at LinkedIn. So when I got to LinkedIn, I knew a little bit about stream processing, and these people came in to actually sell us an early stream processing system, and it was very cool. But we didn't buy it because we had no data to put into it. We actually didn't really have real-time data. What we had was a bunch of log files. And they said, well, that's no problem. You can take your log files, a few hours after you're done collecting it, and you can feed it into the stream processing system. And we said, well, that's not very compelling. We can feed that into our data warehouse too. And so we didn't buy it. But then as soon as we actually got to having real-time coverage of data with real-time feeds, the most natural thing you want to do is process that data. And my view on stream processing is actually as something relatively general. Right? So I actually see it as a way of taking logs, right, which we've already talked about at great length, and transforming them into new logs. So that's what it is to me. And so this view is very similar to that kind of trigger or materialized view in database world. And for people who subscribe to the log, they don't really know. They need not know whether it's derived by some processing or whether it's the original log of data, right? So everything is just kind of a real-time feed to them. And this is a little different. Like when people talk about stream processing, they may mean many different things. A lot of people mean something that kind of computes something, approximately and throws away all the results. What I actually mean is just the ability to do, real-time derived data processing off of your primary feeds. And with that definition, this is, stream processing is actually a generalization of batch processing. Batch processing is where you get kind of all your records and you process all your records to produce all your output. And that's in contrast maybe to request-response type processing where you get one input record and you produce one output record. And stream processing is actually just a generalization between those two where you take some number of records of input and you produce some number of records of output and you control the granularity of that input and output. And having that control is really important for real-time data where you obviously can't wait until the end of the stream, right? If you're subscribing to a feed of page views until your company goes out of business, there is no end to that feed. But if you think about it, there's no end to any of the feeds for any of the data that a company like LinkedIn has. All of our data is real-time feeds, and none of it has any end. It's always being changed, right? All of our processes are real-time processes, and they all change data continuously. So when we do batch processing, like run Hadoop jobs, we're kind of arbitrarily picking some frequency, like maybe we run our jobs, every 24 hours. But that's really just an arbitrary window that we've chosen to run our reprocessing of batch computation. So having something which gives you more control over that window is actually really important, especially for domains that are low latency. I don't think this is that important for kind of offline analytics or ad hoc question asking. But it is really important for domains that have latency requirements. And I think for most businesses, this ends up being a substantial portion of their code. So for LinkedIn, I would say probably 50% of our website is online, meaning request response processing. 25% maybe is offline, meaning Hadoop stuff. And 25% I think really is in the domain of low latency asynchronous processing. And that's the domain that stream processing can help with. So 25% I think is actually a pretty good chunk of our stuff, and it's it's a percentage that's least well supported I think right now by infrastructure. So the examples of the types of problems that are really applicable to this are anything around monitoring. And I use monitoring in the most general sense of the word of detecting any kind of problem or computing any kind of results about your operational environment. Security, which I talked about. So typically if people, any kind of abuse or whatever of a website, you need to detect that in real time and shut it down. Content processing. This is very general. So at LinkedIn, we ingest jobs, we crawl news articles, we have all these different types of content. People update their profile, and we do all kinds of processing and normalization to try and get good, clean representations of the the professional world out of that. And that turns out to be a really complicated and algorithmic set of processes. And so that's that's another great domain for this stuff, as well as recommendations, newsfeed, ETL, all that kind of stuff. And So when I talk about stream processing, there are systems that do this stuff. We've built one called SAMHSA. There's also one called Storm. Both of them integrate really well with Kafka, and they both do a really good job of kind of taking these input logs and allowing you to process them in real time. You don't, of course, actually necessarily need a stream processing system to do stream processing, but it can actually solve a lot of the problems that you run into if you try and do this in your own application without any kind of framework to help you. So it can manage state for you. It can give you a better partitioning model for data and so on. And if you're interested in this stuff, we've written up some details on SAMHSA that you can read about kind of some of these problems that it solves for you. And the high-level architecture for SAMHSA is essentially the lowest level is this feed that's in Kafka. We use Yarn, which is a framework in Hadoop, and then we provide a layer on top of that that allows lots of jobs to run on a shared cluster and process logs or feeds. And how this contributes to our overall infrastructure, if we were to zoom out very far, I've kind of drawn this log in the middle. That's the integration point for data. And then each of these systems, along the top row, we've got systems that are either storing data or serving some kind of derived view of it. We can take any of those feeds of data and we can process it in our stream processing layer and feed it back into the log for live serving. Likewise, we can take everything that's in the log and project it out into Hadoop for offline processing, and any of those offline processes can publish back feeds of their own data for real-time serving. And all of this stuff is available for kind of monitoring and graphs. And so we have this central point of integration around this log. And in a sense, when I say this is, our whole system is kind of like one big distributed database, this is what I mean, right? This is actually not that different from what the internals of a distributed database would look like, with some kind of commit log, a bunch of real-time serving indexes, a stream processing or trigger mechanism, as well as some offline, background maintenance tasks down in the Hadoop layer. So it's kind of an interesting analogy to think about. And that's the end of my talk. If you're interested in this stuff, I have a blog post on the same subject, which is actually even longer and goes into a great deal of detail around how logs are used in systems, how you can build systems around this stuff. It gives more examples around the stream processing stuff, as well as talking about more details of the data integration problem. And then if you're interested in how Kafka works, I haven't really said much about it. I talked about some attributes, but there's a ton of documentation that will tell you, how it's built and how everything works on the Kafka site. And if you're interested in SAMHSA, there's a website as well. Both of those systems, of course, are open source and they're Apache. And that's it. I'm happy to take any questions.
All right. Hey, this is Ben Lorica. We do have time for a few questions, and there are lots of questions, actually, definitely more than we have time for. So I just grouped them together. So here goes. So the first set is more high level. The first set of questions is more high level. So since the system you described is the centrality of a log, based on your conversations with other people, is this type of architecture something other people are doing?
Yeah, it does seem to be that way, right? So I think the people that this has been most appealing with is web companies, and I think web companies are maybe pretty early on in this use of real-time data. If all your company wants is to get the data into an offline system like a data warehouse, and you're pretty happy with an offline processing cycle of 24 hours or 8 hours or whatever it is, then having this kind of this ability to get real-time feeds is maybe not as compelling. The log concept is still kind of cool and nice, but it just doesn't provide you as much value. But I think for a lot of web companies, they're doing some type of ingestion or processing, and they're probably very similar to LinkedIn in that a large portion of that processing is much more naturally online. So yeah, if you go to the powered by page on Kafka, you can get some long list of companies that are really doing this kind of log-oriented data flow. And you'll see, yeah, there's a couple of kind of traditional enterprise companies and a ton of younger web companies, and partially probably for the reasons I described, and partially just because this stuff is new and those companies are more experimental and willing try new things quicker.
So the way you describe the design and evolution of Kafka, you guys really, I think my interpretation is you guys definitely looked around and decided what you needed didn't exist. So you went ahead and built it. So in some ways, the architecture of Kafka was driven by some observations you made. So I guess what you're saying is this observation of the right architecture is now being made by many other companies.
Yeah, so it's obviously a lot easier to do if you can get the infrastructure, if you can just download the infrastructure instead of building it, right? And I think this general problem is a problem that a lot of companies actually face in a really serious way for the reason that I pointed out, right? They can get access to all these really cool free distributed open source systems, but actually getting them all working together and getting that data flowing through everything is a real problem.
So there's lots of questions around comparisons. So
okay.
So basically, people want to ask questions about how does Kafka compare to this messaging system, or how does SAMSA compare to Storm. So maybe if you can just address, just roughly,
yeah, sure.
like for example, the Kafka thing.
Yeah, absolutely. So let me address both of them. So the biggest difference between Kafka and traditional messaging systems is that Kafka is built much more like a distributed file system in a sense that maintains one of these logs. And so what that means is, and data in Kafka is always immediately persisted, and we do replication, by default. And so that's a little bit different from most traditional messaging systems where they may have some of these features, right? They generally do persistence if you turn it on. They do replication maybe if you configure it, but especially like replication would be kind of a real bolt-on with enormous performance implications, and you would only turn it on for one really critical data source and only if you monitored it very closely. So I think there's two differences, right? One is, we were coming from a more distributed systems background. I think, messaging systems, their architecture tended to evolve much earlier, and so they kind of missed out on some of the good distributed system stuff that's more recent. I think we were kind of advantageous. I guess it's like last mover advantage. We had the advantage of starting after that stuff. The second bit is really just some of the implementation details, right? Like handling persistence well turns out to be really important for offline data, right? Hadoop, data warehouse, anything which is taking large volumes of data but may not take it for hours at a time sometimes. That turns out to require obviously a large amount of persistent data while you wait for Hadoop to come and load it. That's something messaging systems don't do well. As evidenced by how rare it is that actually ETL is built on top of messaging systems. Like it makes sense that it would be, but in practice, if you look at most companies, it's not. And I think the reason for that is because it's actually relatively hard to make an ETL cycle built on a traditional messaging system reliable. We kind of looked at what that would mean, but like for example, you can't do things like reload your data, which is obviously much easier if you have a log where you just go back in time and reload that same data. So that's probably the biggest difference. Is really that kind of architectural difference and the kind of scale and throughput and distributed system stuff between Kafka and other systems. I think if I were to be totally fair, the downsides are I think the Kafka is more work to set up initially. It has a larger footprint, right? Like we depend on Zookeeper, which requires several servers. So it really makes sense if you're going to try and run it as a platform for a number of applications where, having two different moving pieces, the Zookeeper piece and the Kafka piece, is kind of worth the price of admission. If you're really just going to have like one message queue for one application, then maybe it's overkill. So that's probably the trade-off or downside.
So I guess the follow-up question is SAMSA and Storm.
Yeah, absolutely.
I assume that you guys must have been using Storm or some other system before, no?
No, so they happen somewhat in parallel. So the biggest difference between SAMSA and Storm is SAMSA is built also around this log concept, and so it's a mechanism for transforming logs into other logs And that makes a lot of the other implementation things a little easier. It makes it possible for us to do, I think, a really principled way of maintaining large local state with your processing job. So what on earth does that mean? If you imagine, like in SQL terms, it's really easy in a stream processing system to do filtering, like a where clause, and record at a time transformation, like maybe whatever's in your simple select clause. But anything that's like a join or an aggregation, it usually requires maintaining state between records. That's something that's actually much harder to do right in a fault-tolerant stream processing system. And so one of the advantages of this log stuff is that you can actually have a exact log of state changes in your stream process and make that fault-tolerant as well. So you can think of that as having kind of a distributed database in a way that's co-located with your stream processor, so that the database and the stream processor are co-partitioned together. It's kind of a weird concept, but it's very powerful if you're trying to do things like counts or other aggregations. And we've actually written a much more detailed comparison of Storm and SAMHSA. There's a ton of other differences that are about the implementation that are probably too nuanced to describe just over the phone. But if you Google Storm SAMHSA comparison, I'm sure it's like the first thing that comes up. And so that will give you actually a much more nuanced overview of kind of all the pros and cons. We've tried to be pretty fair about what we're really good at and what we're not good at yet.
So a bunch of people are asking about the relationship between Kafka and Zookeeper. I guess people are wondering, Zookeeper, obviously, I guess Zookeeper must be up and well managed for Kafka to work, but
yeah, that's right. So Kafka depends on Zookeeper. So I guess our intention is the different types of these systems have a different operational footprint, right? So maybe Hadoop is very complicated, has lots of moving pieces. It's true of Hadoop, HBase, a few other things, a lot of moving pieces. And so you use them kind of organization wide. So hopefully that operational complexity pays off. Kafka is not as complicated. We really have two moving pieces: the Zookeeper setup, which may be shared with other applications, and then the Kafka machines themselves. But that is more complicated than most other messaging systems, which just have the messaging system. And we use Zookeeper to do our own internal leadership election and kind of shared configuration between the Kafka nodes. This is one of the advantages of kind of being the last mover in the space, is you can take advantage of a lot of the kind of like modern approach to building distributed systems. It makes a lot of the stuff you're trying to do much easier. Otherwise, you have to essentially implement Zookeeper kind of inside your system to build that. And so we've saved a lot of time by just depending on it.
So we've gone slightly over time, so I'll just ask one last question that I think a bunch of people on the chat alluded to, which is, where do you guys come up with your names?
Yeah, so I guess we have two internal approaches towards naming. One is boring acronyms, and that's universally popular in software engineering, and we have those. And then the other is weird words that don't necessarily mean that much. And I've always gone with the weird words because at least it's memorable. But in this case, we did actually have some kind of very vague justification. There's usually some very vague justification. So we thought, well, Kafka is going to be it's going to be maintaining a log. Another word for a log is like a journal. So it's kind of like a writer system. Like all it does is take your writes. And so we thought, well, we'll come up with a writer name. And so we came up with a writer name that sounded at least kind of cool. So that's the extent of the story. I wish it was more clever than that, but it's not.
All right. So we'd like to say a big thank you to Jay Krebs for presenting a great webcast and sharing his knowledge and expertise and experiences with us. We'd like to thank all of you that attended our webcast today and hope you